All right, let's get started. So, what we did Tuesday was the language of things about dynamics, and we solved some very simple two-degree of freedom problems applying those. And then I'm sure you have reinforced that language of things in solving a homework problem. Today is really the first day for this topic because we're going to talk about the equations of motion for a rigid body. Okay? In 3D. So far, Tuesday we had a 2D, but it's 3D. Okay? So, there are many things we can consider, but normally this is probably for those of you in Changwon who have done wonderful drawing on the ship. Don't laugh. So this is my ship, okay? Normally the center of gravity might be around here. Like that. But it's quite convenient sometimes to put location of origin of the coordinate system where the captain's room is. Okay? So I'm kind of putting it this way. Okay? So the center of mass and center of coordinate system, they don't coincide in many. It's true in automobiles, it's true in ships, it's true in airplane. Okay? So we make this guy an abstraction. And then let me just write it down here. Sorry. And I'm going to do the following thing. The inertial reference frame is XYZ. Okay? And the unit vectors attached to is I, J, K. They don't move. Then we have a body here. The origin over here is, I call O. This guy moves with this body. And so that from here to there, I will call the distances R. Maybe I will call R0. And then I will look at the small mass away from this this guy. But mass center is, say, for exaggeration, mass center is over here. So what I do here is from here, I go first to that way, which I will call RC. And from here to there, there is a small mass Tm. and then I will call just R as a vector. So that the position vector, total position vector, R is R0, capital R, plus RC plus R, where RC is XCI plus YCJ plus GCK, and R is just XI plus YJ plus GK. Okay? So the unit vectors over here is IJK. Sorry for those of you Changwon, if you can see these small fonts. I don't know whether they can see it or not. Can you see these small fonts?
Yes.
Oh, good.
It's small.
It's a small, but you can see it. Great. Get your eyesight 2.0 on each side. So the velocity is just simply time differentiation of that. So that's V0 is this body moving relative to the reference frame. Okay? And then I have here, like that. Now, let's look at this guy a little bit carefully. Then this RC dot, I can write it this way, okay? XC, YC, GC, I, J, K, and dotting each of those. Okay? You might recall from your undergrad that the unit vector that is moving, the unit vector here is moving with the body. That time the rate of that is angular velocity of that body cross with its own unit vector. Okay? So, okay. What that means is I use an analogy here that is RC, that is omega cross RC. Okay? Similarly, for other part is simply omega cross R, where omega is expressed in terms of moving body fixed coordinate system, so that omega xi plus omega yj plus omega gk. Okay? Now, let me have few words about it. The coordinates are fixed in body fixed coordinate system, little x, little y, little g. Therefore, when you differentiate, you have to differentiate this times that one, and this derivative of this one. And since they are constant, for example, xc dot is 0, yc dot is 0, gc dot is 0. Okay? Similarly over here. But that's not the case, this omega. When I differentiate this omega, the omegas are changing because it's a changing angular velocity. So what you have there here is the omega, okay, x dot I plus omega y dot j plus omega z dot k, and the kijk is also moving. Therefore, what you have here is omega cross let me see. Let me write it down correctly. In this case, what I have here is omega x, omega y, omega z, and then I dot j dot k dot, and this guy is really, I call here is omega, okay? There are many symbols. I use 0 over here, which means you only differentiate the coordinate omega x, y, z, and plus, when you do that, you have basically omega x, omega y, omega z, and this guy is, you can write it down, say omega cross I, j, k, k, like that. So using this, then what we need is acceleration, right? And acceleration A, this position. In other words, we are getting the position vector R, velocity V, and acceleration at this small mass. Okay? Remember, no mass and no equations motion in this lecture, okay? So we are focusing on very small mass, and since if we know these three things, we can talk about the equations motion or other kinematics for this particular small mass. So that one is we differentiate this guy. So over here, then we have a V0 plus omega cross, you might call here is RC plus R. Now the A is now A0, which is differentiation of this guy twice. All right? And then first what we do here is we differentiate this guy omega. So omega dot, and then cross RC plus R. And then what we have here is we're going to utilize this guy right here, okay? Which means that omega cross RC dot plus R dot, and that turns out to be omega cross R. Like that. And let me just get rid of this guy. So here I can write out that omega cross that. You've seen this in your undergraduate physics, right? And second year dynamics course. Okay? All right. So that is acceleration. And the question is, how do I write the equation for this small mass? Okay? And I'm going to erase this. For this small mass, there might be some force acting on small mass applied forces acting on it. Okay? This could be some forces acting on it or moment acting on it as well as gravity forces. Okay? So then I have here is a 4 small mass. It's mass times acceleration. So this is dF minus mass times acceleration, which is this guy. Very simple, right? For the small mass. But what we are looking for is not really small mass over here. We are looking for the mass for the total body, right? So what we do here is we just integrate this guy over volume. Okay? So we call that as F, total F. And what happens here is A is moving around all the different places. Okay? So it turns out when you work that out, and then all we have to do is you change this guy. These two guys are independent of location, right? The only difference here is this one and that one depends on XYZ. So those are the only ones, that is the only ones that you have to be concerned with. So now let's just say dm and A0 plus omega dot RC dot plus R plus omega cross RC plus R. And let me just use a big bracket and dV. So these guys are independent of XYZ. Okay? It doesn't depend. This is the only one dependent on XYZ. So now you might recall, all right, if I integrate, let's say there's a constant, this omega. It's very, very important for me to emphasize. So omega here, say this is omega prime, omega here, okay, and anywhere. So omega is in other words, if I am a rigid body, which I am not, but pretend I'm a rigid body, and I go through this rigid body motion, my angular velocity here, 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 they are all same. Or put it the other way around, okay? If I have an angular velocity, I'm moving this guy. This is you can view as a rigid body, okay? I'm moving this box, it's like that. So if I measure angular velocity over here, angular velocity everywhere inside, outside, they are same. Okay? All right? In a body. In a rigid body, that is. Okay? So the angular velocity is constant, same everywhere in integrating this guy. So angular velocity doesn't change. RC doesn't change. A0 doesn't change. So I can call this guy is also independent of XY. And that is independent of that. This is independent of that. So that leaves only R to be integrated. Okay? Now you will recall if I integrate this guy with respect to this O. Okay? So I integrate. Then you might recall, say, okay? So I got it, I take it back. I don't need a dV because instead of dV, I will look here, Tm. Okay? So that was my mistake. This has to be Tm. In other words, I'm integrating Tm. So what is a Tm in reality? Tm is rho dV. Okay? So if the density is the same, then it becomes a volume integral. So this guy, when I integrate our entire domain, they drop out. Okay? So the net result here then is I get F minus, I get a total M, right? And A0 plus omega dot cross RC plus omega cross RC. And that is my equations motion for translation. Okay? Okay? So, you see, you are in grad school, okay? You probably haven't seen this much other than just some circumstantial cases. So it's this equation for rigid body. It's general, so you can use this equation for when the origin of the this thing is not coinciding with the center of mass in the coordinate system. And that's very typically true in automobile, airplane, ships, you name it, all the transportation vehicles. Okay? So that's the easy part. Now let me move to not only this guy, all right, goes both this way, that way, and this way. That's three translation equation motion. This guy also rotate. And rotate in 3 dimensions. Rotate this way, rotate that way, rotate this way. So we're going to have 3 more degree of freedom to characterize the equation's motion. This one characterized when this guy is moving in coordinate, XYZ coordinate. But even when this guy is not moving around, there will be a rotations And that's, in fact, that's what makes you guys seasick anyway. It's not this guy moving that makes you seasick. It's the rolling. Okay, so this guy is what we call rolling. And when I have this guy moving around, this guy is pitching. And this guy is yawing. So sometimes you just call roll, yaw, and pitch. And not only that, it's this rotational motion, moment and the angular momentum equations are really closely associated with the stability of the ship, meaning that whether the ship will fall this way, okay, or this way, okay, and just go berserk like that, okay. So most of the cases, the ship go under through the rolling. Okay. Now, let me just before I go on this equation, I want to say a few physics about it. That is not a really fantastic. Okay, so that is just a cross section of a ship. Okay, and if I look at from the top, I have this one. So here I have, say, this guy. This guy is mx. That's rho. And here, this guy is. Normally, this guy is the marine guys put the axis this way toward the water depth. But it doesn't really matter. X, Y, Z. Okay. So that one is here. So X, this might be X, Y. Okay, so MY. And then this pitch might be MG. So let's just say for this moment of inertia in principle thing in MXX, IXX, IYY, IGZ. This is the so now tell me, for those in Changwon, you guys might know more about this thing in the class, students. Okay, wake up, okay? If you are drowsy, go out and come back. Which moment inertia would be the highest in general? It's II or IXX, IYY, or IGZ in general? Anyone want to volunteer from Changwon? Which one will have the highest moment of inertia for typical boat? Okay, what about here? Anybody has guess? Huh? G? It depends on the type of a ship. How about catamaran? Huh? Catamaran is, this is looking at from the top of the ship. In catamaran cases, it's like that. And this would be MY. In typical ship, in this case, actually MY is bigger than MGG, MXX. In typical traditional, say, cargo ships or oil tank, stuff like that, this is highest. It goes like that. So what it means here is it's going to fail, the ship will overturn due to this motion, which is what your intuition is. This is easiest to make the ship roll over, right? So you can see somehow intuitively, we're going to study next Thursday. Intuitively, the stability mode of a ship is somewhat related to the smallest moment of inertia. Okay? You can imagine if this guy is wide like catamaran, it would be very difficult to roll over this ship, right? Because it's get wider and wider. Then when it's wider and wider, this guy is going to increase. In general, you can see the smaller value of a moment of inertia somehow is related to the rollover situation. Okay? All right. Same thing with the automobile. Okay? If the automobile is very high, not the low, it has a easier way to roll over. And that's where the word rollover came from, the roll. So like a Volkswagen or something like that. Vis-a-vis this guy, so let's make it a little better, a little shorter. So this guy has a very small moment of inertia relative to this guy, or this one. So the higher this guy, it's more prone for rollover. So if you're afraid about the rollover, then just because it's sports utility looks good, don't buy it, because it's going to roll over much easier when you go through the mountain. Okay? So we're going to learn something about these things next Thursday. Okay. Now what we need is to get the rotational motion. Okay? Let me see whether I can save any of these. So the moment equation is, we studied Tuesday, that is, moment equation is, we just simply apply the moment like that. And in moment equation, we have to do one thing. What do we have to do? In translational equation, we just sum the forces, but in moment equation, there's one thing you have to do. Anybody remember? It's only 2 days, right? It's only 2 days. You remember what we have to do in moment equation? Huh? I hear something, P.
Point.
Yeah. You have to specify with respect to what point you are computing moment. Specify the location about which you are summing the moment. Okay? So I'm going to do that. This point is O prime right here. Okay? So O prime. All the apply the moment. Okay? Then what I do here is minus, right? RC plus R, because I'm measuring moment of this mass, inertial moment, from this point, which is RC plus R, cross dm A. Okay? That's for little dm. All right? Now, what I need is, I need some of this guy. So I do d, m, o, okay? Here dv. And then I have here is, I will say, instead of dm, I have rho dv. So I have rho RC plus R cross A acceleration times dv and integral. And that would give me my rotational equation. In other words, I know some of you are thinking ahead. No, this is not what I have seen. I've seen very vaguely something like that. I've seen something like that. Why this crazy guy, Casey Park, starts from here? Okay? I know you are thinking about that. Okay? The reason is this is too simple. And this is good when you are writing equation motion with respect to this center of mass. When this is not center of mass, there's some complication. So it's better to go all the way back, start from what we call first principle, right? This is what we call first principle, right? So in other words, whenever you are in difficulty deriving something, go back to the first principle. And I'm trying to do from the first principle. Okay? So let's not worry about it. Okay, that is exactly what we are doing. So we only know when we integrate something's really, in other words, when we integrate, that was a 0. However, let me just put this guy back into the game. I was saving this guy and I erased it. So this guy is MO dot minus, this guy is rho RC plus R cross. Let me see whether my memory serves me right. A0 plus that. And I have here omega cross R plus RC plus R. So here there was only one R. Now we have here R multiplying this one, multiplying this one. Okay? So the question is, R cross something else, okay? Oh, I'm sorry, here. That, and there's this term, what are they? Okay? So here it's 0, but that may not be 0. It could be something else. Okay? So this one can be expressed as following, okay? As a following. That is ijk, okay? And I have j, omega x, omega y, omega z, that, like that. Sorry, where J is moment of inertia. Here I use I, so let me use I. So I is following. Ixx, Ixy, Ixg, and Iyy, IYZ, IZZ, and symmetry. Like that. This is a moment of inertia matrix, okay? So that, and this one turns out to be, okay? Let me just write down here. Turns out to be something like this. IJK, I will call omega tilde matrix, very special matrix. Like that, where omega tilde matrix is a very funny matrix. It's 3 by 3. The diagonals are all 0. And here is minus omega z, minus omega x, omega y, and omega x minus omega y. So this is the skew symmetric. It's a funny matrix. Okay? Now I have a question. Can you guys are capable of carrying out this all vector cross product and integrate and get to here or no? Do you know how to do that? Or you want me to show you at least for one? Say yes or no. You've seen this before, right? Right? Ah. Okay. Let me just expand this thing. Now I can erase this part. That is, if you work it out, this part, I will have why this guy after a while quit writing? I just don't know. Here I have that's better. Okay. So it comes out to be this way. Okay? So the integral, here's Ixx, is integral this guy. Like that. Similarly, all the rest of the expression. All right. So we got this expression, that expression. So we need to carry out the whole thing. So let's carry out that one. All right? And before I do that, let me just say one thing about a little bit of physics. No, I will wait until I finish this derivation. So let's work it out. Cross product of that one, cross product of this one, cross product of that one. But I only have this one, that one, and that one. Okay? So there are additional terms. So additional terms, so we're gonna, let's just separate this guy. So since that RC and RC doesn't really matter, let's just work it out RC part. So what we have here is rho RC cross A0. And then next one is omega cross RC, omega dot cross RC. Next one is this one, which one is plus omega cross RC. Okay? So remember, omega is the same everywhere in rigid body, okay? So omega from one point to the next point is the same. Omega here, omega there, it's all same, omega. Okay? So omega is a constant in integrating. In other words, this is constant, that is a constant, so the whole thing is a constant. Okay? So the result here is this guy, I can simply rho dV integration is mass. Okay? And I have here RC, okay, cross A0 plus omega dot plus RC plus omega cross RC. That one. The other term, we already worked it out here. Okay, this term, and this term. So here what I have here is following, okay? I can write in terms of a vectorial quantity. So I have here minus m, that vector. And what I can do here is I can do and it's minus. And let me just do it in the right way. Big bracket I omega x dot omega y dot omega z dot plus skew symmetric 3 by 3 matrix that over here, okay? And I omega x, omega y, omega z, okay? And big bracket, which is 0. All right? So that, let me just get rid of this guy. And I say here's apply the moment m0 dot. And that's equal to 0. And that is this equation. Okay? Now, if, okay, RC is equal to 0, that is, you choose the origin of coordinate system at the mass center. Okay? This means choose x, y, z at mass center. Then I can express this guy like that. So now I have here ijk, here ijk. Take all the unit vectors away. I have the equation that you already know. That is I omega dot plus omega skew symmetric I omega equal to m. M means this guy, okay? This means apply the moment. So you can see the equation that you've seen in your undergraduate or some other courses. A very simple and special case of a general equation. And you have to include this thing to get the equation of motion right. Okay? And let me just rewrite equation for corresponding. This is a rotational equation. And the translational equations motion is m plus omega cross RC plus omega cross RC minus F equal to 0. And this is translation equation. Okay? So we have here we have a 3-degree of freedom. Here we have a 3-year rotation. and total 6 degrees of freedom. Okay? The remainder of today's lecture, I want to go back and say something about angular velocity. And angular velocity is a very difficult concept in three-dimensional problem. Okay? Now, anybody, including the you student at Changwon, volunteer to tell me how do you characterize angular velocity? Anybody would want to volunteer? What is angular velocity? You can tell. What is velocity then? What is velocity? See, once you know the equation of motion, you've got to be able to express in words, because that's what humans communicate. You don't communicate. When you are both asked, tell me the velocity. This is 10 meters per second. But you have to be able to explain, what do you mean by velocity? What do you mean by acceleration? And what is the definition of a velocity? Anybody can say in words? Come on. You've been computing velocity all your career, right? What is a velocity? The one way back there, what's your name? 이광훈? 이관훈? 건훈. 이관훈. Mr. Lee, tell me what is velocity? Okay. What he says is velocity is a vector. It's got magnitude and direction. It's very simple. Velocity is, say, v, normally vxi plus vyz plus vzk. Right? So it's got magnitude. And it's got direction. I'm sorry, Jay. That's why we use the vector. The velocity has a magnitude and direction. Not only magnitude, it's just one magnitude, which is absolute magnitude. It's got the component decomposition of velocity into different directions. Okay? It's got direction and magnitude. Now, angular velocity is the same way. So it's got the magnitude and direction, right? So then question is, what is omega x, omega y, omega z? You know what the vx, vy, vg, right? Right? How can you say in words? What is a vx? Vx is the amount of the distance this particle travels, okay, in a unit time, right? That's how you learned in the physics. And that's why physics is very important. And when you say, that I already know, okay, let me sleep. Okay. Now, pick it up with the words because that's much easier for you to communicate. Your boss, when you graduate and go to industry and work, your boss want to be told by you in words, whatever you do. And tell me what you do. Okay, I'll show you all this great equation, great numbers, and great computer graphics. No. That's not how you communicate to your colleagues and your boss. You need to be able to express in words. I'm serious, okay? So then, what is omega x? Let me call, when Korean students don't volunteer, so I have to call the names. Okay. 이권훈, 이동석. Yeah, what is the angular velocity? Say omega x.
Omega x is angle change per unit time.
Angle change per unit time. Is that correct? Everybody agrees with you? Angle change per unit time. You think so? You learned it that way. Okay. In undergraduate, two-dimensional cases, that is true. Okay? So x and y, and you change this guy, theta and theta. The rate of change theta dot is, in this case, omega g. Right? So omega g is not exactly angle change. You can say angle change, but it's a spin rate. Spin rate. It's been only about a month since Winter Olympics finished, right? Less than a month or about a month? So you will see plenty spin, right? Especially in the figure skating. It's the rate of spin is angular velocity. Okay? Because suppose this is the true, then, and my spin is doing this way. It's very difficult to express in terms of angle changes, right? It's only when you are aligning with the coordinates, you can say things. But when you are looking at, which is exactly what this omega is, combination of omega x and yz, okay? It's very difficult to express in terms of angle changes. In fact, angle changes is not unique. But it's the spin rate. In other words, omega x is a spin rate, okay, around x-axis. Omega y is a spin rate around y-axis. And omega z is a spin rate around the z-axis. Because what you are saying is correct, angle change. Okay? Then I can see the angle change can be gotten from omega x dt. Right? That is not true whatsoever. You cannot get it that way. Okay? There lies the problem and challenge. You cannot obtain the angle change this way. In other words, if your definition of angular velocity is true, you should be able to get the angle change by integrating omega. Right? It doesn't happen that way. You all know that, right? In three-dimensional case. This is not true. Okay? So the definition that you learn in undergraduate or high school physics is no longer in three-dimensional cases applicable. Okay? So strike those things out from your brain. Okay? And it's only spin rate. Okay? And we are going to learn how to get theta from omega, but it's not that as simple as this one. Okay? All right. So now let me, in the remainder of I have about 15 minutes, right? Because I started at 45. Okay, 10 minutes. In remainder 10 minutes, let me talk about the angular velocity, concept of angular velocity. So remember, it is a spin rate, okay? It's not the angle change. So what happens here in general, when I change from, say, this axis, say XYZ, and some other axis, so there's something omega which spins this XYZ, and afterwards it moved to a x prime, y prime, z prime. Okay? Then there's a relationship on the either coordinate as well as a unit vector. This is I, this is j, this is k, this is I prime, j prime, k prime. Then I prime, j prime, k prime is related to 3 by 3 matrix and I, j, k. Okay? Suppose I, j, k is fixed. Okay, that is they don't really move. In other words, I, j, k are in inertial reference frame. Okay? The vector unit vectors attached to inertial reference frame, their time rate is changed is 0 because they are not supposed to rotate. Remember, inertial reference frame? They are not supposed to change. They can go only at constant translational velocity. Therefore, this guy is at 0. And I will call this guy as R. And R is 3 by 3 matrix. Okay? Then let me just express this guy as like that. And this one is not only I prime, but I prime, j prime, k prime. Okay? This is 3 by 1 unit vector. Okay? So now, if I say time rate, I have r dot I plus ri dot. But this guy is a 0 because they are really fixed in inertial reference frame. Now, let's go back and look at this guy. This guy, I can multiply R inverse I can write it this way, right? Say the inverse exists. So I have I is R inverse I prime. So I'm going to substitute it over here. R dot is R inverse I. Okay? All right? Do you remember what I introduced the other day, last Tuesday? I dot is omega cross I. Okay? And this, I can write it this way. Like that. Okay? Turns out, where omega, this funny skew symmetric matrix, this guy. Like that. Okay? So comparing this guy to that, omega 3 by 3 skew symmetric matrix is this guy. Okay? But it turns out this is what we call orthonormal transformation. In orthonormal transformation matrix, I inverse is the same as I transpose. Okay? So this guy is, and that's definition of angular velocity. Okay? That's how you get angular velocity. Now, let's try the things that you already know, which is the two-dimensional cases. So in two-dimensional cases, this transformation, now this G1 is the same. Okay? In this case, you're accustomed to you know this matrix, right? Right? Now, if I just add a K, all I have to do is I augment like that. And that I call R matrix. Okay? So now if I differentiate this guy, I get theta that out, and I have a minus sign theta. I just use a S cosine minus cosine and minus sign 0, 0, 0, 0, 0, right? Okay? Okay? Now this by definition, since I have only the K component, spinning this component is K component. Only I have this component. The Y, X, omega X, omega Y are 0 because they don't, this axis doesn't spin. That's why spin is important. Okay? So this one is the same as 0, 0, minus omega Z, 0, 0, 0, 0, 0. Okay? And Ijk. This one is theta dot minus SC minus C minus S 0, 0, 0, 0. Remember, ijk is R transpose I. Okay? So transpose is this guy, and transposing means this becomes column, this becomes second column, etc. So I have a C minus S, S, C, 0, 0, 0, 0, 1, ijk. When I did carry out, this guy will be, sorry, I'm not writing. So this guy is a minus SC plus SC, that's 0. Second one is a minus S minus S squared plus C squared, that's 1. Okay? And this one is a minus C, but that's minus 1. And the rest of them are 0. All right? So, looking at this one, then it's clear. Omega z is theta. Now, I have to make sure this guy is in fact the case. It might be transpose instead of omega, which means this guy is a plus and minus plus. Okay? Okay. In that case, this is a transpose. So by comparing these two, then you know in this case omega z is theta dot. So the one that you know for two-dimensional cases is a very special case of this relationship. Okay, and I take it back. This has to be transpose. Okay. In other words, I don't know whether I got it right. This is. I thought this is minus and plus, but it's not. Minus, plus, minus. Yeah, true, correct. That one is according to this formula, R transpose. So R transpose, right? Yeah, transpose is this guy. So that's 0, that's 1, that's minus 1. So its definition is omega transpose. Sorry about that. But the point here is this is a rather general expression. And if you did the right things by computing this guy, you can compute the component omega xyz. Miraculously, when you do that, this is another thing. When you do the computation, there may be some non-zero terms showing up, small non-zero terms showing up in real computation, and that's a computational error. Okay? When you compute this guy. So that's how in real life, sorry I overused the time, the relationship between the unit vector transformation matrix, the rate of that, and combination of that is related to that. Okay?